It's my real honor and pleasure to kick off this seminar series this year. It's a tremendous series to get to really see what's happening out there in the energy landscape, and it's just my joy to be able to share with you some of the things that we're working on in our laboratory. And as Professor Wyant so aptly explained, the context of today's talk, what I'll be describing is developing sustainable pathways to fuels and chemicals. It's about being renewable and being sustainable, which means that we're going to start off by talking about fossil fuels. And there's a very important reason why, and I want to go through this list where we're going to talk about what fossil fuels provide for us today. So I want you all, as we go through this list, I want you to think about petroleum, think about gasoline. And first of all, let's recognize that while many of us think that there might be issues long-term in using fossil fuels in terms of their abundance, they are incredibly abundant today already. I mean, they are all over the earth. We're getting just 5 terawatts just from petroleum alone out of the 17 terawatts that we're consuming globally, which is a massive amount of energy, a massive amount of power. So it's a very big worldwide resource, but it's also got many other wonderful properties. For instance, it has a huge energy density. I mean, if you think about it, let's say you think of a Honda Accord or a Toyota Camry. I mean, you could just fill up that gas tank and drive yourself 500 miles nonstop. 500 miles, right, on one tank of gas. So the energy in just one tank of gasoline in a car like that is approximately equal to, say, the potential energy in 1 million gallons of water. Imagine 1 million gallons of water 200 feet above us. Okay, that head pressure. Or you can think of it as the electrical energy stored in 80,000 iPhone 6 batteries. Okay, 80,000 iPhone 6 batteries, just one tank of gas in a Toyota Camry. It's also got a high power density. It's not just got loads of energy. You can deliver that energy very quickly. You can power just about anything you can imagine. Automobiles, trucks, shipping vessels across the Pacific, commercial, military, aircraft. And if you want to convert the power transfer, just filling up your car at the gas pump, you convert that into electricity units, it's about 5 megawatts. That's what's running through your fingertips as you're holding onto the pump, right? Think about a nuclear reactor. A typical nuclear power plant is about 1 gigawatt. That's like 200 Toyota Camrys getting filled up with gasoline at the same time. It's a crazy amount of power. Yet, despite all this high energy, high power density, it's chemically stable. I mean, we all drive bombs. You drive it around in a car. It is a bomb, but nobody thinks of it that way because we've engineered it to be very safe. So it's a very safe form of energy storage, too. It's also very easy to store and transport. If you go from coast to coast driving your car, it's about 3,000 miles, right? There's about 100,000 miles of gasoline pipeline across the United States, so you can transport it with ease as a liquid fuel. Of course, it can fit into any shape and container you can think of. Let's talk about cost. I mean, the cost of gasoline right now, even in the state of California, my goodness, it's already down in the $2.50 level these days, right? So if you look across the U.S., it's about $2 to $3 a gallon. And maybe that seems expensive to you, maybe it seems cheap. I think it's pretty inexpensive when you compare it with other consumer goods, like how about bottled water? Or how about milk? How much does a gallon of milk cost? A gallon of milk at Trader Joe's is right now more expensive than it is to get a gallon of gasoline at Chevron. How about a gallon of oranges? I mean, a half gallon of oranges is more expensive. So, this is a heck of a lot of value that we're getting for these fossil fuels. And then, of course, there's convenience. And this is something that I like to bring up. I don't know about you guys, talking about techno geeks and things. I like to time myself at the gas pump. That's kind of how I entertain myself. I get there, I put in the pump, I hit it, go, and I look at my watch. I'm very precise on the timing. And it never takes me more than 3 minutes to fill up my gas tank. Never more than 3 minutes. It's usually closer to 2, in fact. And I think to myself, let's say I'm traveling, I'm at an airport, my phone battery has completely died on me. I'm switching between flights, and I only got 3 minutes to plug in my cell phone. Imagine that. How much energy am I going to get out of that? Can I even boot my phone? 3 minutes? Whereas I can fill my entire family in the car and in 3 minutes go from a completely empty tank of gas to something that get me from here to Los Angeles and maybe to San Diego, right, in 3 minutes time. It's pretty impressive stuff. So the point is, while my whole talk is all about using renewable energy and sustainable energy, we have to remember this key set of attributes. Really, any future energy technology needs to compete with this. Okay, if it doesn't, it's going to be a tall order to get a massive shift in the right direction. All right, so how do we go about thinking about doing such a thing? So the engineering approach is to think about a black box. Think about a black box that can do something that you really want it to do. And so we're going to look at this black box. We're going to feed into 3 things that the Earth has in abundance. We've got a lot of sunlight, we've got a lot of water, and goodness knows we've got a lot of CO2 in the atmosphere and climbing. Okay, let's feed those 3 things into this black box. We're going to ask that box to break some bonds and reform some bonds for us. And what are we going to make? We're going to get one stream of oxygen coming out the end. And then we can imagine a long list of very important molecules that we are already using at a massive global scale. Okay, most of these things that you see are fossil fuel derived. Okay, we're talking about hydrocarbons, we're talking about alcohols, hydrogen, carbon monoxide. Well, what do you do with this? Well, simply put, any one of these could operate as fuels. Okay, so this would be a sustainable pathway to take the things that we're all breathing in the air literally right now and converting it into fuels that we can burn. Or you can use them as chemical products that go directly into as chemical outputs from the chemical industry. Or if you're not making the thing that you want, you can still plug that back into some other mode of operation in the chemical industry. So these could become chemical precursors that can then go into the infrastructure to make the chemical that you do want. Okay, so we can make an awful lot of things if this black box works. The question is, well, what's inside the black box? And there are a lot of possibilities. This is where we're only limited by our own imagination and our own creativity, so long as you don't violate the second law of thermodynamics. That's all I ask. Okay? So what I want to talk about today are some schemes, and I'm going to represent just to widen the scope of what you might think about. But there's photobiological schemes, so those of you who are interested in biology can think about approaches of engineering organisms to do what you want to do to make fuels from sunlight. You can think about some photochemical means to do it. You can imagine grabbing a bunch of mirrors, shining them onto a hot spot, and then driving temperature-pressure-based reactions with heterogeneous catalysis. You can imagine grabbing solar cells that produce electricity and running them to an electrolyzer. Okay? Many different ways, clearly not an exhaustive list of opportunities. The question is, what do we want to put inside that black box? There are so many options. What I want to talk about today are these two options that we're looking at here, where we're talking two distinct devices, where one device generates electricity like wind turbines and solar cells. The other device does the chemistry, these chemical transformations that we're describing. Okay, so for instance, in this example, you can grab the CO2 that comes out of the exhaust of a car, feed it into this device, you grab renewable electricity, and you convert it into fuels and chemicals. If you make it into a chemical, you can make it into, let's say, ethylene. That ethylene goes into a high-density polyethylene process, and then from there you make milk jugs. So you take the CO2 we're breathing into a solid form that is now recyclable for the rest of its life. Or you can make a fuel that you burn in a car just like we normally would, and as long as you capture that CO2 out of the tailpipe and put it right back in the process, now you've got a net zero carbon emission. So this could either be net neutral or net negative in terms of carbon emissions. Another option is to have an integrated device where you're kind of combining the solar cell with the catalyst in this process here, and now you're pretty much taking the solar cell-ish looking thing, you're shining light on it, you're dunking it under water, and you can either use that process to split water into hydrogen and oxygen immediately, or you can flow in some CO2 from somewhere to make things like methanol or propanol or gasoline or what have you. So it's still a debate as to which is kind of the better way to go, but I'll tell you this, that either way you absolutely depend on good catalysts to break these bonds and make these bonds to make these processes happen. So where does it fit in? So here's a kind of a process diagram that my group is starting to come up with to think about where all these flows can go. And on the top left, what you're looking at are energy sources, right? So we're talking about power plants that could be burning biomass or coal or what have you to produce electricity, hydro, solar, wind power, okay? So you have all this stuff goes into the electrical grid. On the other end down here, we have the uses. We have transportation, producing fuels, producing chemicals. And what you can imagine is these devices I was just talking about in here, these are renewable ways where you can electrolyze these types of molecules. So you can electrolyze water to make hydrogen and oxygen. You can electrolyze CO2 to make gasoline, diesel, or methanol or other chemical products. You can electrolyze methane, where there's an awful lot of natural gas these days that one could also electrolyze in principle to make those types of products, or electrolyze nitrogen and make things like ammonia. Okay, that's the basis for fertilizer. And so the point is that if you can develop these types of technologies, there's a way that it can already fit in to our modern energy economy and our modern chemical infrastructure. So you can make all the things that we need, but of course these are renewable pathways if your energy source is coming from either directly from solar photons or if it's through the electrical grid. And the nice thing is that if you combine these in the right way, you can actually get things that are greater. In other words, something that's more synergistic. For instance, this power plant, okay, you burn your biomass, what do you produce? You produce CO2. Well, that CO2 could go into the atmosphere, or it could go into a reactor where if you provide renewable hydrogen from this electrolyzer that's coupled to renewable energy, that hydrogen can react with the CO2 to go make fuels and chemicals, okay, with that output CO2 from the power plant. And by the way, that electrolyzer, if it's making hydrogen on one end, it's going to be making oxygen on the other, right, H2O. So that oxygen, what do? You can feed it right back into the power plant, and then you can do an oxycombustion process, which is a more efficient way to burn the biomass and get a higher efficiency electricity. Okay, so there's many ways that this can couple. You can also imagine electrolyzing nitrogen and making ammonia. So you're basically ripping apart the bonds of hydrogen off of water, sticking that hydrogen onto nitrogen. You make your ammonia, and what do you do with that ammonia? You feed the crop that can go into that biomass power plant. Okay, so there's many synergies that one can imagine with all of this. Now the question is, though, well, how much does it cost? And that's a really good question. It's really tricky because these technologies are not already operating at scale. So how do you start projecting what this thing would cost if you were to build it out at a large scale? So we took part in an analysis with DOE and a number of partners to try to answer some of those questions, at least with one type of technology. We were thinking about this photoelectrochemical hydrogen production. So this scheme where you shine light onto a device and it splits water into hydrogen and oxygen for you. So we came up, what do you do in chemical engineering? This is our capstone course that we teach our students. It's chemical engineering plant design. So you basically design a chemical plant to mass produce something that you want to produce. So when you design an entire chemical facility, you generally start with the reactor. You design your reactor, and then you build out all the auxiliary systems, the pumps and the compressors and the heat exchangers and all the separation units. And so what we did is we designed 4 different types of reactors, which we call type 1, type 2, type 3, and type 4. Where type 1 and type 2 were kind of these particles that were suspended in bags with water in them. And these were more photovoltaic type materials, either with solar concentration or without solar concentration, where again, all these materials are absorbing sunlight and taking that water and splitting it to make hydrogen and oxygen. And we asked ourselves the question, well, how much does all of this cost? Well, DOE sets this target of $2 to $4 per gallon of gasoline equivalent. So 1 kilogram of hydrogen, just for the record, is about 1 gallon of gasoline equivalent in energy. And these are the prices. You can think of this as a gallon of gasoline. Would you be willing to pay $1.60 for a gallon of gas? Oops, or would you be willing to pay $3.20 or $10.40 or $4.10? So it's really interesting. You can see without even having the technology in hand yet, we can actually see what it might cost if you do the full-blown techno-economics if you were to scale it up with some assumptions on your device performance. And then the neat thing is that then you can take those assumptions and do a sensitivity analysis. So for this type 4 reactor, if you assumed it was a 15% efficient process where your panels cost about $300 per square meter and lasted you 10 years, we come out with a price that was about $4 a kilogram, which is a little bit on the expensive end, granted, if you want to compete versus fossil fuels and versus gasoline, but still kind of reasonable. And it turns out that if you went from 15 to 25% efficiency, you could lower that cost significantly down to $2.90. Okay, and you would take a hit, of course, if it were a lower efficient device. Here's the sensitivity to cell cost, here's the sensitivity to lifetime. And what's not shown here is if you start taking all 3 of these things into account and optimize all 3 of them, then you can really lower the cost into a very attractive range. And so that's really what drives a lot of our research group, is realizing that, hey, we need higher efficiency, we need lower cost materials avoiding precious metals, and we need longer lifetime stability is very important here too. And that's really what drives a lot of the fundamental research that we do in our labs. So having said that, what are the problems that we're working on? So there's kind of 4 major thrusts within our research group. One thrust is electrocatalysis. How can we develop catalyst materials that can speed up these chemical reactions and be as efficient as possible? How can we take protons and electrons and make hydrogen? How can we take protons and electrons and stick them onto CO2 to make hydrocarbons and alcohols and other important fuels and chemicals? Of course, you need a source of protons and electrons. Where are we going to get them from? We want to oxidize water to release O2, and that's where we get our protons and electrons. You read all these reactions left to right, that's the fuel production direction. It requires energy to make that go. We want to get it from renewable sources. The fact that they are electrochemical reactions is very favorable because we can grab that electricity directly from solar and from wind, which we all know has a big issue because they're intermittent resources. But that's great. You can just feed intermittent resources into these processes and make fuels that can last you months or years if you wanted. Okay? These chemicals are pretty stable, as we already talked about. We're also in our lab very interested in driving these reactions right to left, because that's how you get the energy back out of these chemicals and into electricity if you so choose. So these are just some of the reactions that we're working on to catalyze these chemical transformations. We're also very interested in putting them into devices. And so these are some of the other themes that we're working on in our group. We want to put some of these catalysts onto solar cell type materials so we can shine light on them and immediately start producing the products that we want. We also want to put these types of catalysts into devices such as this one I'll talk about in a bit, these regenerative fuel cells. These are grid scale storage devices where you can feed electricity in when the sun is shining, split water into hydrogen and oxygen, have it there, and then when the sun goes down, you can feed it right through the same device and get the electricity back out so you can have 24/7 electricity to the grid. And then the last area of the lab, we're also very interested in thermal catalysis. This is a little bit more plug and play with the conventional chemical industry, which uses temperature and pressure to drive chemical reactions. So here we have taking carbon monoxide, carbon dioxide. Again, these are the same types of reactions that you're seeing up here, but instead of written in electrochemistry lingo, they're written in more conventional chemistry lingo. And the point is we want to use heat and pressure to make these types of products, like higher alcohols like ethanol or methanol. So today I'm really going to be touching base on these three areas. All right. So what I like to do with the remaining time here, this hopefully gives you kind of a sense of what the area is of these renewable and sustainable fuels and chemicals. And I'm going to give you kind of snapshots in 4 different areas that are relevant to what I just talked about to kind of dig into the science a little bit more. And so first I want to talk about developing hydrogen evolution catalysts, and more specifically, how do you develop precious metal-free catalysts that can compete with the precious metals? And then how can you integrate them with semiconductors so we can do this direct solar process? Another area I want to talk about is taking some of those catalysts and putting them into devices such as water electrolyzers so that we can just flat out replace platinum with these non-precious metal catalysts. I want to say a little bit about these newer devices for grid scale energy storage. Okay, these are devices that are completely precious metal free, and again, we can use this type of technology to store electricity from the grid, from renewables. And then finally, I'll touch on catalyzing carbon dioxide reduction and just talk a little bit about how we convert electricity into carbon-based fuels and chemicals. All right, so clearly we're not going to have time to go through all these in great detail, but I want to give you some sense of how we think about solving problems in these areas. So let's talk about hydrogen evolution first. So the first thing you need to know about hydrogen is it is one of the most important industrial chemicals that we use today. And the proof is in the pudding. We're talking about the order of 60 billion kilograms per year. 60 billion kilograms per year. How many people are there on the face of the earth? 7 billion. So that means on average, every man, woman, child on the face of the earth is responsible for 9 kilos of hydrogen made per year. Okay? There's about $100 billion process. About 2% of global energy goes to just making hydrogen. Where do we get our hydrogen from? We get it from methane. We get it from natural gas. So it's a steam methane reforming process, gives you about $1 or $2 per kilogram, gives you that hydrogen. And where is that hydrogen going? Why are we consuming so much of it? Well, it goes to really 2 places, split about 50-50. Ammonia synthesis, which is of course fertilizer. Okay, so it goes to feed people. That's a pretty good reason to make hydrogen. And the other is crude oil refining. This is how we upgrade our crude oil to make all the products that we use today, whether it's jet fuel or gasoline or diesel, etc. So now the question is, can we make the same type of hydrogen from a solar-based process? Well, sure, we already talked about that. You shine light onto these photoelectrochemical cells. This is the reaction you drive with a delta G of positive 1.23 EV. And if you do that, then in principle, you can make the exact same chemical reagents that we already use to make fertilizer and oil upgrading. But then if you can make it this way, then it really starts to make sense as an energy carrier to drive cars and to power homes, etc. Okay, so that's the idea. Now, to talk about how we develop catalysts. So the question is, how do you develop catalysts that can make you hydrogen from water without using precious metals? So let's talk a little bit about the chemistry here. This is all electrochemistry. Again, we want to take protons and electrons, stick them together to make H2. This is what our electrochemical cells look like schematically. I won't get into the details. What is important is how to read the data, because I'll be showing you plots of this variety. So let's be pedagogic here for a second. This is a current versus voltage curve. Okay, this is voltage on the x-axis. 0 is defined right here in the middle. And when you're at 0, this is the reversible potential actually for this reaction on the scale that I'm showing you today. Meaning if you give me an electrode and hold it at 0 volts, the backwards and the forwards reaction are going at exactly the same rate. So if you want to make hydrogen, then you'd better tilt your voltage negative so you can favor the H2 production. And if you want to oxidize hydrogen, then you tilt your voltage to the positive side to split that hydrogen into protons and electrons. So I'll be showing you lots of data that looks like this today. This is schematic data where you're basically tilting the voltage negative, 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 and voila, then you start seeing a negative current. Negative current is an indication of hydrogen being produced. The more negative the current, the faster the hydrogen is being made. And that's what it looks like schematically. This is what real data looks like on this voltage scale. You can see that with no catalyst, there's no current being measured on this current versus voltage trace. Here's with a catalyst. You see it's nothing, 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 and then takes off. And what makes for a good catalyst is you want to get this data pushed to the right as much as you possibly can. All right, so this is how you read the data. How does this process actually work? Let's think about this for a moment. Think about water, and you have some catalyst. And in that water, let's say you're doing this in acid, you have protons floating around in solution. So there's two types of mechanisms. This is really the simplest reaction you can write that involves more than one species. Okay, it's as simple as it gets. It's 2 protons and 2 electrons goes to an H2 molecule. And so really there's only 2 possible pathways. And the interesting thing is, despite the simplicity, despite there's only 2 options, it turns out that there's still a massive debate going on as to which is the mechanism that actually takes place. 200 years of science, and we still don't know. So let's take a look at this and see if we can come up with some understanding. So this one's called the Vollmer-Tafel mechanism, where you have these 2 protons that are floating around. And the first thing that happens is this proton lands, it grabs an electron from the metal and forms this hydrogen atom sitting on the surface. Okay, let's say that process, the exact same process happens again, but it's just on a different spot. So now you have 2 hydrogen atoms. Then they move around, they move around and find each other. Ooh, I'm going too fast. Okay, there we go. They move around, they find each other, form a bond, and take off. Okay, that's called the Vollmer-Tafel mechanism. This Vollmer-Herowski mechanism goes very much the same way, where the first proton comes down and lands and grabs that electron. And now the second proton, rather than landing on an empty site, it lands on top of the first atom, and then it forms that molecular H2 and takes off. Okay, so they're very, very similar mechanisms, but there are, it actually can have a big implication as to how well your catalyst works. But the key thing is, I want to point out that if you look at both mechanisms, they have something very much in common, and that's this hydrogen that's landing on the surface. And you could ask yourself the question, if I want to make a good catalyst, you would think that it might matter how strongly or how weakly that catalyst is bonding that hydrogen. In fact, that's absolutely correct if that thought was crossing your mind. It doesn't matter which mechanism it goes. That's still a very important metric. And this is something that was figured out by Roger Parsons about 50 years ago, where he basically did some pencil and paper theory with thermodynamics and kinetics. And this here is just activity. Think of it as activity on the y-axis. Higher is better. And he basically says, hey, look, just tell me the strength, the delta G of how strongly that hydrogen is bound to that surface. And the closer you are to 0, the better. If you bind it too strongly, it drops off. If you bind it too weakly, it drops off. You want to be right near delta G as close to 0. That was a very profound recognition that he had made 50 years ago. The only problem was it was very tough to utilize that information to develop new catalyst materials, because if you made a catalyst and you wanted to make this measurement of this delta GH of that hydrogen, it takes longer to make that measurement accurately than just making hydrogen off of it in the first place and seeing is it any good or not. But then 50 years later, we're in a different world, and now we can actually use a computer to calculate this for us. You can use density functional theory methods and calculate. Let the computer do the work for you. Let it calculate all these delta GHs for a bunch of different materials. And so on this plot, we're looking at the same type of plot, but now these are all experimental data points on the y-axis, measurements of activity, versus this delta GH calculated by the computer on the x-axis. And what you see is this volcano-type relationship emerges, even though that all these data points are coming from all these different labs around the world for the past 50 years. Okay, they're following a certain trend. So that tells us we're starting to understand something about this reaction. The only problem is that all the best materials are here near the top, are all precious metals. So how do we make catalysts that are just as active as the precious metals without any precious metals at all? And this is where we look to nature to help us solve this problem. And in fact, this is work from Jens Norskov and Berit Hinnemann. So Jens Norskov at the time was at the Technical University of Denmark. He's on the faculty with me, one of my colleagues in chemical engineering. And they basically did the study of looking at nitrogenase and hydrogenase, which are known enzymes to make hydrogen, and they have no precious metals at all. And they found by theory that, hey, these are pretty active systems. And they said to themselves, well, how can you mimic this type of active site on a solid state material? And so the answer was they looked at these molybdenum sulfide materials, and particularly at the edges of molybdenum sulfides. So when I was a postdoc at the Technical University of Denmark, we had synthesized a bunch of these nano triangles of molybdenum sulfide with lots of edges, and we were able to show that these were very active catalysts indeed. We were able to provide experimental confirmation on the theory that theory predicted this to be good. It was in fact good. When I started my research group here at Stanford, then we went hog wild, cranking out all kinds of different nanostructures of molybdenum sulfide, with each of these nanostructures having lots and lots and lots of edge sites. And we found something that we expected. The more edge sites you engineer into these materials, the more active they are for catalysis. And I can show that to you with this data here. Again, current versus voltage. Here's these nanowires going to these nanoporous materials, to these molecular clusters, going from 1 to 2 to 3. You can see that this is a pretty good catalyst here. You only need about 1/4 of a volt to get this thing to drive about 10 milliamps per square centimeter of current density. And then option 2 is about 50 millivolts closer, and then you can go even 50 millivolts closer to 0. We're just marching our way towards to the right. And remember, that means it's a better catalyst the further to the right that you go. So my students, and postdocs, as they were creating all these different nanostructures, as I was describing, of molybdenum sulfides, and kind of understanding how to engineer these things to be better and better for catalysis, we also asked ourselves the question, well, how can you start integrating these things onto semiconductors so that you can do some direct solar photoelectrochemical water splitting? And so then my student Jesse, what he did is he took a P-type silicon wafer, which you can just order commercially. They're really cheap these days. And in the clean room here at Stanford, at the nano fab, made a PN junction, so just like a solar cell. Then he deposited about 3 or 4 nanometers of molybdenum metal onto that surface. And then he did it up in H2S at 250 degrees C, and that forms this MOS2 structure on top. So this is the cartoon version. Let me show you the real life version. Here's some cross-sectional TEM images. I can zoom in a little bit. What you're looking at here, here's the silicon wafer I was describing. Here's the MOS2 on top. MOS2, you might notice, has this layered structure very similar to graphite. Okay, but it's with, instead of graphite being this, carbon, two-dimensional form of carbon, this is like a sandwich of sulfur, molybdenum, sulfur, and then you're stacking sandwiches on top of each other with van der Waals gaps in between. These 2 layers in between, this here turns out to be a molybdenum silicide. So when you deposit molybdenum metal onto silicon, you form a silicide automatically because of the heat. And then this is molybdenum metal. Okay, so there's got pretty much a 4-layer structure of silicon, molybdenum silicide, molybdenum metal, and MOS2. So the question is, well, how well does this thing perform for solar water splitting? So he takes this device, encapsulates this in an epoxy, sticks it into an electrochemical cell, and shines simulated AM 1.5 radiation. And what do we get? We get pretty good performance. Here's the current voltage curve. And there's something really interesting I want to point out, that notice that we're actually getting this current density to the right of 0. I had mentioned a few slides ago that if you want to make hydrogen from water splitting, you have to be on the left of 0 to favor the reaction in that direction. Well, it turns out because the silicon, right, you're shining light on it, you're exciting electrons from the silicon, you're using these photoexcited charge carriers, that's how you can actually get these things to move to the right, so to speak, on this plot. That's what that indicates. So this is great news. This means we're actually getting our 10 milliamps per square centimeter, which, by the way, keeps up with the solar photon flux at about a 10% efficiency. And now we're getting these positive values of 0.16 volts, whereas all the other values I was showing before in the dark were in the negative direction. My student, undergraduate student, Kara, in the lab, she developed a means to do some quantification of the hydrogen coming off. And what she finds is that, to within error, 100% of our electrons moving through the circuit are in fact going to hydrogen. So we know it's not some corrosion process or some parasitic process going on. How about stability? This was really exciting. This is all done in sulfuric acid. And we looked at this sample at times t equals 0, and after 100 hours of constant illumination in sulfuric acid, and we find that these curves absolutely overlap one another. So even though it's only 2 to 3 nanometers, this is tiny, it's 2 to 3 nanometers of molybdenum sulfide, not only is it providing really good catalytic activity to the surface, it's also protecting the silicon, which would completely fall apart under these conditions otherwise. So the good news is that it was active and it was stable, but there's only one issue that we saw. The way this molybdenum sulfide grows, there's not a whole lot of edge sites because it's growing so flat across the surface. And I told you earlier that's the edge sites where the activity is for hydrogen. So how do you go about putting more edge sites on there? So this is where Jakob and Jesse worked together. And Jakob had developed these MO3S13 clusters that I pointed out that had lots and lots of edge sites. And we literally just spray painted these things down onto the same photoelectrodes I was showing you before. So you just spray it down and you're just basically adding a bunch of edge sites, and voila, what are we doing? We were able to move this point another 110 millivolts to the right to get the same current density of 10 milliamps per square centimeter. And then my student Tommy entered the game, and he was really interested in working on phosphides. So he developed some phosphide materials, put them down onto silicon, and got even better performance still. Now we're at positive 0.35 volts versus that hydrogen electrode, continually marching to the right. Now, where does this all stack up? So now on this plot, I'm showing you those 3 samples. This is the straight MOS2 on silicon. Here's the MOS2 with the MO3S13 on silicon. Here's the cobalt phosphide on silicon. And they're getting better and better and better, but you can see where the room for improvement is. And this is pretty much the gap that we have with non-precious metals versus platinum. Platinum is still king. There's no question about that. And you can make a judgment call. You can say, well, these are less efficient, but they're a lot cheaper because there's no precious metals. But I think where we need to be is where platinum is, but with a non-precious metal. I think efficiency is just too darn important. We don't want to sacrifice that. So that's why in our lab we're continually working to make better catalysts and then put them onto silicon, again, sticking with non-precious metals. So let me switch gears and say, well, what else can we do with these catalysts? So they're making hydrogen pretty well. Can we replace platinum in electrolyzers? So here's what another one of my students, Desmond, has been working on. Desmond's been working on these types of devices. These are, he works on several types of devices. That we're looking at is a proton exchange membrane electrolyzer. So it's pretty much a fuel cell that you run in reverse. You put electricity in, you can split water to hydrogen and oxygen. And his goal was to replace the platinum inside this membrane electrode assembly. So he took all these formulations that I was describing before, these molysulfides and molyphosphides and molyphosphosulfides and other formulations. And now we're going to look at current versus voltage in a slightly different way. Here's current now on this axis. Here's voltage on this axis. And you can see this is platinum and iridium. So platinum and iridium are respectively the best catalysts known for in acid. For hydrogen evolution is platinum, and for oxygen evolution is iridium. And so where you want to be is you want to get as much current density as you can with the lowest applied voltage. And indeed, this iridium platinum system is still king, but we can see what happens when you replace the platinum with some of these non-precious metal systems. You can see that, yes, you do lose something. You lose about 0.2 volts, but you've completely got rid of precious metals on one side of the membrane electrode assembly. And that's absolutely worth something. And so again, these are also very stable formulations. We need to keep making better catalysts if we want to march along this direction, try to match this performance, but entirely precious metal free. Let's talk about new devices for grid-scale energy storage. So everything I've talked to this point is a way of making chemicals and fuels, taking in renewable electricity. But there's also something to be said for just using the chemicals as onboard storage, right? So again, when the sun is shining, you want to just store that energy on the order of hours to weeks to months, and then be able to feed it back in to get electricity out and maintain 24/7 power. And so DOE's targets in terms of capital cost are about $100 a kilowatt hour for grid scale energy storage, and that is a really tough target to meet. So here you can think really universally about any way possible to store energy, thermal ways, electrochemical ways, mechanical ways, with flywheels or pumped hydro, molten salts, what have you. And we think regenerative fuel cells actually have quite a promise because of all that we talked about earlier about how fuels have so much intrinsic energy in them and so much intrinsic power density that you can get out of them that they might make a good fit. The only problem is that the best regenerative fuel cells that are used today all contain precious metals. And so we went about developing what's known as an alkaline exchange membrane unitized regenerative fuel cell. It's quite a mouthful, but it's basically a type of device that could be inexpensive because you can make it with no precious metals whatsoever and could use these chemical transformations to keep that electricity moving. So here's the idea. You make this fuel cell. It's a fuel cell that, again, is both a fuel cell and a water electrolyzer, and that's what makes it a regenerative fuel cell. And it's all in one unit, therefore it's unitized. And the fact that it's using an anion exchange membrane means it can operate in base instead of in acid, and base is generally less corrosive for non-precious metals. So Desmond went about developing this type of a device that could be either an electrolyzer or a fuel cell and toggle back and forth. So he built this thing with 2 types of catalysts. One's based on nickel and one's based on manganese oxides. Okay, same type of physical contraption that you can hold in the palms of your hand. And this is some of the data just to give you an idea of how it performs. The equilibrium potential is at about 1.2 volts, meaning if you give it more than 1.2 volts, it will split water to hydrogen and oxygen. Okay, this is, again, current versus voltage. Or you could feed hydrogen and oxygen into it, and it'll give you a voltage and a current out. And the interesting thing about this particular report, it was the very first report ever of a low-temperature unitized regenerative fuel cell that was completely free of precious metals. The only issue here was the round trip efficiency. I shouldn't say that's the only issue, but that was a major issue. At 30 to 40% efficiency, which we've improved on a bit since then, but if you really want grid scale storage, you need to be closer, I think, to 80% round trip efficiency. So that's what we're trying to do, is by making better catalysts, then we can basically shrink the gap between these two curves and get closer and closer to 1.2. That's how we're going to improve the round trip efficiency. And finally, let me just say a few words about catalyzing carbon dioxide reduction. All the chemistries that I've been talking about to this point have been involving water and hydrogen and oxygen. What about, we talked about this early on, we want to convert CO2 into fuels and chemicals. So let me just start by saying it's a much harder reaction, and I'm going to tell you why. And the interesting point is it has absolutely nothing to do with the thermodynamics of the reaction. So on that voltage scale I kept talking about before, this hydrogen reaction we see here, when you hold your electrode at 0 volts, again, that means backwards and forwards go exactly the same rate. Interestingly, if you're trying to stick protons and electrons onto CO2 to make carbon monoxide or methane or ethylene or some alcohols, interestingly, those equilibrium potentials are almost exactly the same and very close to that of hydrogen. Which basically means if you give me electrons that are energetic enough to go into protons to make H2, those electrons are just as energetic enough to go into CO2 to make gasoline or to make alcohols or to make other hydrocarbons. So thermodynamically, there's no issue with the overall thermodynamics. The problem's all in the kinetics of the reaction. And I want to elucidate that by looking at this particular reaction here. Let's say you want to stick 8 protons and 8 electrons on a CO2 to make methane. So you start with CO2 coming down onto a surface. These are calculations done by Andy Peterson and Jens Narsko and others. Okay? So here's CO2 coming down onto a surface. Imagine hitting it with 1 proton and 1 electron to make a carboxy, COOH. You hit it with another proton and electron and it attacks this hydroxyl group to make water. Now you're left with carbon monoxide sitting on your surface. Another proton and electron, you make HCO. Another proton and electron, you make formaldehyde. Another proton and electron, you make a methoxy, which is OCH3. And now the next proton and electron, wherever it hits, is going to dictate the product that you make. If you hit this oxygen down low, you make methanol. If you hit this methyl group up high, you make methane. And I had said that we're going to look at this methane pathway. So you hit this thing up high, you make your methane, you have this oxygen atom sitting around, you got to clear it off your surface. So you need 2 more protons and 2 more electrons to make water. Now you've got an empty surface, you can go back to square one. And my point is, boy, did that take a whole lot of time to talk you through this whole reaction, right? It took a lot of effort just to say it. Imagine actually the catalyst to do it, right? I mean, this is 8 protons, 8 electrons, a much more complex reaction pathway than, say, making H2. And by the way, this is just one of many possible pathways that it could be. So the real challenge is how do you make a catalyst that can do every single one of these steps just right and very efficiently? We're all familiar with the concept of a rate determining step. If one of these steps is bad, kills the whole catalyst. So you need that catalyst to just be perfect for every possible scenario there. So when we went about investigating this chemistry, one of the things that we brought to the game was doing some reactor engineering, developing fundamental tools, some reactors that we can study this chemistry in greater detail than had been studied previously. And really one of the main things that we were after is developing a cell that allowed for really detailed product identification and quantification. And so there's a lot that we've learned from this. My students, Kendra, Tasha, and David here were the original first graduates from the group to work in this area. And I just want to talk about some of the products that we saw on copper. You just take a copper foil, you just purchased a pure copper foil, polish it up a little bit, put it in our reactor, and these are the 16 products that emerged from that reaction. And it's really interesting. I mean, first and foremost, let me say that at the time that we had done the study, only 11 products had ever been reported in the history of humankind for studying copper. We saw all 11 of those in one consistent set of studies, plus the five additional ones that you see here. And having said that, you look at this list, it's a really great list of chemicals. I mean, it's formate, it's carbon monoxide, methanol, and methane. These are they all contain just 1 carbon. Then you've got the C2s like glyoxyl and acetate glycolaldehyde and ethylene glycol, acetaldehyde, ethanol, and ethylene. And then here are some 3 carbon products, hydroxyacetone, acetone, allyl alcohol, propanaldehyde, and 1 propanol. So 1 propanol is really interesting. You're talking about 18 protons and electrons. Okay, you're grabbing 3 CO2 molecules, pumping in 18 protons, 18 electrons. That's way more than the methane I was just talking about, and linking these molecules together to make this one product. Copper did all this. This is just a copper, kind of an off-the-shelf copper, just polished up a little bit. all done at room temperature and ambient pressure. It's really a great list. It just kind of gives us a sense of what could be done if you can engineer a catalyst material that can be selective to the products that you want. And one of the big problems here is not only, I'm not showing you how inefficient it is, the reaction rates are way lower than we want them to be, but the other problem is that all 16 of these kind of emerge simultaneously. And then you've got a separations problem to deal with. So from a catalysis point of view, you want better efficiency and you want selectivity to the products that you want. The last thing I'll say about this is that I want to just circle a few of these products. These are some of the most massively produced products that you'll find worldwide. I mean, these are all in the billions of kilograms a year production rate. We already talked about that, so everything I've circled, every man, woman, and child on Earth on average is responsible for at least 1 kilogram a year of production. And that just gives you a sense of if we can make these types of molecules in a renewable, sustainable manner, this could actually start putting a dent into the energy problem. So with that, let me summarize and conclude. Hopefully I was able to convey to you that I think that renewable fuels are very promising. It's very challenging, but it's very promising. In our research group, we've been developing a lot of catalysts, particularly those that make hydrogen with non-precious metals, which I focused on today. And it's not just about making the catalysts, we've been integrating them into devices, into photoelectrodes, electrolyzers, unitized regenerative fuel cells. These are all potentially very interesting technologies from a scale-up perspective. Also, I think this area of catalytic CO2 conversion could be really important because this could in principle be a carbon negative technology and the worst case scenario, carbon neutral. And with that, let me just thank my wonderful team of researchers who've been part of this. I've been kind of pointing them out along the way. Also thank our funding agencies, particularly the Global Climate Energy Project, which has funded a lot of the work that you saw here today, as well as the US Department of Energy. So I thank you all for your attention. I'm happy to take any questions.
We do have time for a few questions. We like to start by tradition with student questions first. Student questions?
Anything you'd like. It's all fair game.
Back there.
Seeing the development of the electrical vehicles, do you think that there is...
I'm sorry, seeing the development of what?
Of electrical vehicles.
Oh, of electric vehicles, yes.
Like Tesla cars, do you think there is still space for hydrogen?
Oh, absolutely, absolutely. I mean, let me scroll up here. This might take a moment, but obviously I had quite a few animations. Let me just say a couple of things. I mean, first of all, I'm a huge fan of electric vehicles. There's no question about that. I mean, they will definitely play a very important role. We also have to remember that fuel cell vehicles are electric vehicles. I've never met a fuel cell vehicle that was not an electric vehicle because what does a fuel cell produce? A fuel cell produces electricity. And that's what ultimately drives the car. So every credible design that I've seen for a fuel cell vehicle is actually a battery vehicle. The batteries just happens to be much, much smaller than a Tesla would need because you're getting your long range out of the chemical storage in hydrogen. And so, so a fuel cell vehicle, just to give you, a number, if you put in 5 or 6 kilograms of hydrogen, you can drive that car generally 300, 350 miles. On 5 kilograms. And remember, 5 kilograms of hydrogen has the energy content of 5 gallons of gasoline. So how can you drive 300 miles on kind of 5 gallons of gasoline? That's because the fuel cell is much more efficient at converting that hydrogen into electricity than an internal combustion engine is in a typical car, wells to wheel. So I absolutely think that batteries are a huge part of it. We have to remember that there's over 1 billion cars on Earth, and they're just used in different ways. So I think from a personal automobile, the consumer is going to choose what's right for them, depending on how they use their car. Are they the type of jump in a car and drive to Lake Tahoe every weekend, or are they kind that sticks around urban areas? But we also have to remember there's other modes of transportation. For instance, trucks or ships, taking a ship across the ocean or a long distance trucking. In fact, the ExxonMobil report for A View to 2040 says that personal automobiles and light duty vehicles, the amount of energy consumption for those is almost flat for the next several decades. All of the growth is coming from heavy duty transportation. And I think, and while batteries can certainly be used in heavy duty transportation, that's a much taller order. So I think, the long story short is that I don't see them as competitors at all. They're complementary, and I think they have to be complementary. If we're asking any one technology to replace fossil fuels for us, we're in a really bad shape. I prefer to think of it as 12, 15, 20 technologies that each contribute their 2%, their 4%, their 8% to the problem. You add all of that up, and you can start putting a dent into fossil fuel usage.
Right up here on the left.
Yeah. So you were talking about the hydrogen catalysis and how Kara demonstrated that all the electrons are being conserved there, and so it's not a parasitic process.
Right.
So then what would be the limiting factor for those catalysts for their lifetime?
So our molysulfides in general are very stable, very, very stable materials, and they work just fine over really long periods of time. What's limiting them is that they're not as active as platinum, and platinum, just to give you a framework, I think platinum is about 5 to 6 orders of magnitude more active of a catalyst than the very best non-precious metal catalysts that exist. And I don't think we need to completely close that gap, because if you're dealing with platinum, you want to minimize, you just want to sprinkle the smallest amount of platinum possible because it's so expensive and so scarce. If it's a free material, then you can in principle just kind of load it up, but there are you run into other problems if you overload the system. So I think you can load 2 or 3 orders of magnitude more non-precious metal material, which means if we want the comparable activity, we need it to be 2 to 3 orders of magnitude more active than we are today. And I think that's how we close that gap.
Great, other questions? Students, non-students? Let's take these two here. So here,
if you polarize your copper sheet for collecting it, can you preferentially collect different reactants?
Different products, absolutely. There is so I certainly didn't dive into those details, but every catalyst that we've made for CO2. So the interesting thing about CO2 versus say something like hydrogen is that when you're converting water into hydrogen, there aren't a whole lot of other products that you're going to make. But if you're converting CO2 into something, you could make a solid, you could make a liquid, you could make a gas, you could make hydrocarbons or oxygenates and different numbers of carbon atoms per molecule. So really there's pretty much anything in the organic chemistry textbook that contains a carbon, a hydrogen, and or oxygen is what could be made. And so steering the chemistry in the proper direction is a big question. And one thing we've certainly found is that the applied potential, whether you apply half a volt or 2/3 of a volt or more than a volt, that not only dictates the total reaction rate of how many CO2 molecules are getting converted, it also dictates the product distribution. And so we look into that data really to grab mechanistic information. It helps teach us about what might be happening, how are these very complex reactions happening on a surface. In the case of copper, with 16 different products, there is no easy pathway on defining one simple mechanism to get you those 16 products. But we do use this the applied potential absolutely has a relationship on the selectivity and the activity of the catalyst, and we use that information to understand it more. At the end of the day, we want small voltages to give us the one product we want and none that we don't want. And so we're trying to use that understanding to tell us how to develop a catalyst that steers things appropriately.
great. So final question?
So you showed us some very interesting possibilities. How long do you think it will take to meet some of the DOE targets that you mentioned?
So the DOE targets for making hydrogen?
Let's say hydrogen, gasoline.
Yeah, that's a great question. I think, we're so far away, unfortunately, that I can't be quantitative with my answer because we have too many needs to develop better catalysts and better devices that implement those catalysts. So, I do think.
Lifetime?
Oh, in my lifetime, absolutely. I feel that way. My crystal ball, yeah. Hopefully, much sooner. But I'm hoping that we might have. So, and it also, I should say, it depends on the product that you make. So the right way to think about this is, in my opinion, take what Tesla did with cars. So Tesla didn't start with their $30,000 car. They started with their premier, most expensive car, small market, right? Small volume, high value. Chemicals is the same deal. So if I could steer the CO2 chemistry anywhere, I wouldn't steer it to gasoline right away because that's a very low price point. Gasoline is so darn cheap, we burn it, for goodness sake, right? So instead of converting the CO2 into gasoline, I'd convert it into, say, butadiene. Butadiene has a value that's 20 times greater than gasoline monetarily, per kilo, but not per, but the market is much smaller, right? So you can start with a process like that and then build scale from there, and as scale increases, then you can lower the costs. So I'm hoping that in the next few years, we might actually see processes like maybe say 5 years, who knows, but let's say 5-ish years maybe, have some processes for some high value chemicals made this way. And then maybe, who knows, 15, 20 years down the line, we can start attacking the bigger markets.
Let's see, one more, let's have to
It's kind of, yeah, it's a different option. Is there a way to produce platinum with a nuclear reaction or?
Is there a way to produce platinum with a nuclear reaction? That's a great question. I wonder. Something I'll have to look into. I have heard of people certainly sending probes into outer space or looking to mine asteroids. There are asteroids out there that are supposedly very rich in platinum, and so the idea is you send these vehicles out there and they will mine the asteroid and bring the platinum back.
jump for you on the list.
Yeah, exactly.
So with that, Tom, thanks very much for our